Minnesota, and our specialty has been operating rooms for about 45, almost 50 years. And we specialize in we call ourselves the air care specialists, but we focus on the performance of the airflow in the operating room, but also how that airflow system really coordinates with everything else in the ceiling. Because as I'll show you, operating room ceilings is probably one of the most claustrophobic, conflict prone spaces in the entire hospital. So there's an interesting balance between medical outcomes, medical device here, and construction processes. So I'm going to start off with an interesting, let me forward here. Start off with an interesting kind of perspective that we start off with. There's a myth out there that operating rooms are pristine and sterile, just like a manufacturing clean room would be. The problem is that can be further from the truth. Manufacturing clean rooms have a certain luxury of design and accessibility that allows them to be very, very clean. You have ante rooms. People are generally very heavily gowned whenever they go in there, and you have the design flexibility to be able to move as much air as possible through these spaces that keep them clean, because usually they're in a rather newer area. An operating room, on the other hand, can be in a very old building, can be in a remodel, can be crammed into a very tight space, and you don't have all the luxuries that you do have in a clean room, especially in terms of the operations going on in there. There's a lot of people coming in and out of the operating room, and the truth is, every single one of those people is a risk to the patient on the table. People are continuously shedding bacteria all the time, even if they're gowned and scrubbed. And some studies have shown that a high shedder can drop as many as 10,000 colony-forming units of bacteria per minute just by walking around. And if you think about the number of people that are in an operating room during surgery, you could easily have 2 surgeons at a table. Let's say we're looking at a knee replacement here. 2 surgeons at the table, a scrub tech handing devices in and out, an anesthesiologist at the head of the table, 2 or 3 nurses out in the perimeter managing the equipment out there, a circulating nurse coming in and out, making sure everybody has the equipment they need, and there might even be a couple orthopedic reps in there talking to the surgeon about how to use the implant they just sold them. There could easily be 10 or 12 people in an operating room, and every single one of them is contributing to the contamination of that space. That is why, even with all the filtration in the world, you need an active air defense system keeping those contaminants that are already in the room from getting to the patient. Now, how big a role does that play in patient outcomes? It's a pretty wide consensus that about 20 to 35% of infections come from the air. This has been determined both by an international consensus meeting, which had the goal of literally reviewing every published article in the English language related to surgical site infection in orthopedics. And they all, 98, 99% agreed that airborne infection is a significant cause of it, and that the source of that airborne contamination is the staff in the room. This study that I'm referencing here from Harvard actually tracked the infection source, not just to the air, by saying, okay, there's a certain number of contaminants in the air, and this was the infection rate, so they must be correlated. They actually traced it back to specific individuals in the room. So for example, they swabbed the surgical wound of a patient, found that there was some bacteria in there, matched that exact bacteria to a bacteria that they swabbed out of the nose of a nurse that was just walking around the perimeter of the room, never even got close to the table. They were able to definitively say that this contamination came from that person specifically. The other side of airflow in the operating room is that, just like in any indoor space, air is primarily responsible for managing the temperature of that space. It's especially critical in an operating room because you have patients on the table that are under anesthesia and more susceptible to hypothermia. Now, in general, you want to avoid hypothermia because it increases the risk of surgical site infection by 3-fold, increases the risk of morbid cardiac outcomes 3-fold, and actually has a 20% higher increased risk of needing a blood transfusion for that patient after the surgery, leading to longer recovery times, more beds being taken up throughout the whole hospital, and just drawbacks overall. That's why there's an entire industry built around patient warming devices, bear huggers, things like that, because patients are too cold. Meanwhile, about 12 inches away from that patient is a surgical team who generally is always saying they're too hot. In most operating rooms, they're saying they're too hot and they need to bring the temperature down further. So it's a weird mix of too cold and too hot right next to each other, and I'm going to show you why that is as we go through this. And the last thing is, we're not only concerned about the safety of the patient, but also the safety of everyone else in that room. From a cardiac or cauterization procedures, there's about 30 cigarettes of smoke produced daily in an operating room. And that smoke is being breathed by everyone in that space. That's why several states have mandated smoke evacuation devices, because nurses that have been standing in the perimeter of an OR for 10 years are developing all sorts of respiratory issues, even though they have no family history of it. And it's because they're breathing smoke in an operating room all day for their job. Now, the solution to these concerns for about 50 years has been laminar flow diffusers. I'm sure we're all pretty familiar with what a laminar flow diffuser is, but all it is essentially a metal box with an inlet in it with a series of baffles within that. The goal of those baffles is to equalize the flow of air across that entire device, so that by the time it comes out this bottom faceplate, it is uniform, non-aspirating, and all the air is moving in one direction, hopefully getting all the way down to the floor and creating a zone of protection around that patient in the center of the room. One thing to keep in mind here is that a laminar flow diffuser is a passive device. It's taking whatever air you're giving it and just smoothing it out. That's the only role that most laminar flow diffuser systems play, just smoothing it out. They're not controlling the temperature, the velocity, any of those other properties of the air, just the flow right as it leaves its faceplate. You can accomplish the same thing with a HEPA diffuser. You just know now that you have a HEPA filter right in that diffuser, and now you're actually providing, for sure, as clean air as you can reasonably get directly over that patient, mitigating any risk of leakage in the ductwork leading from the air handler where you otherwise could have a HEPA filter all the way to the room. One interesting note, though, about the criteria for laminar flow diffusers is that ASHRAE 170 stipulates, which is the code that governs operating room ventilation systems. They define devices that must be in the ceiling of an operating room as Group E non-aspirating, also known as laminar. Except there is no real criteria to which you need to test to be able to be called a laminar flow diffuser. Theoretically, anybody could go in their garage and make a device and market it as a laminar flow diffuser. They could just make a metal box with a faceplate on it and call it a laminar flow diffuser. There is no actual test method that you need to meet, which gets important when you're writing spec languages, because instead of having something with heavy baffling within it like this, you could end up with a diffuser that really is just a metal box with a faceplate on it. There's no baffling within there, no series of chambers. And here's another kind of excuse of a laminar flow diffuser that's just a little perforated ring around the inlet and then just a faceplate on it. This is undoubtedly going to have less uniform characteristics of that airflow coming out than something with an actual engineered baffle within that. Another side note is some of these units could even have cracks and crevices in them that are big enough to literally put a piece of paper through it. And the reason that this is important is because without a good laminar flow diffuser, you can end up with aspiration, where air is actually being drawn back into the device. Dirty air is being drawn into the device, mixed with any clean air that might have been coming out of it, and that air is being delivered then directly over that patient. This is actually a dirt ring on this diffuser in a hospital that we took a picture of aspiration, just like what you would see in an office diffuser, where it's mixing that dirty air and dragging it along the ceiling. Now, the construction side of this is a little bit of a different story and a little bit trickier story. Operating rooms, like I said before, are crowded and very conflict prone. Almost every device in the operating room wants to be very close to the table, especially those devices in the ceilings. You have air, you have booms, you have med gas, you have lights, you have structural components. Everybody really is trying to be as close to that table as possible. And the role of a designer is to mitigate as much of that conflict risk as possible in as little time as possible. You want to be efficient with your time. You want to get your design hours in without going over budget for what you agreed on with your owners. And you want to mitigate as much of those risks as possible. Now, when I talk about risks, what I mean is examples like this: maintenance headaches for the life of the room. What I'm looking at here is a picture of a room that has imaging equipment that's mounted on the ceiling. And because of that, it actually needs ceiling level unistrut running across that ceiling, supporting that imaging equipment. Now, in this example, a mechanical designer said, all right, well, I know I have ceiling level unistrut there, but I need to get my air in there to meet code. So I'm just going to put the diffusers wherever I can fit them around a conflict that I'm aware of, like the ceiling level unistrut. So they pack their diffusers in as tight as possible between those channels, and they put on the plans and say it's good to go. Problem with this is that designer, since they're really only looking in their own lane of the air component of an operating room, they weren't accounting for these other medical devices that are in that space, such as the imaging equipment that's actually hanging from that ceiling level unistrut. Problem with this is really twofold. One, this equipment is now disrupting the flow of that laminar flow air out of the diffuser, essentially negating any protection it was going to provide to that patient to begin with. And also is a maintenance headache for the life of the room, because these faceplates are no longer accessible to clean off any splatter that might get up on the ceiling. And if there's a filter inside these diffusers, that can no longer be changed out unless you're going to take down all that imaging equipment and get it out of the way. It's a huge maintenance headache that's really stuck with them for the life of the room until you do another minor renovation project to fix it. Another risk is unprofessional appearances, and that really is apparent to the ownership at the end of the day and can lead to their disappointment. For example, what we're looking at here is a boom cover that was just a little bit bigger than expected. And so now it overlapped not only onto some framing, but also onto an adjacent light, meaning that this light is going to be a pain to get at and access if ever need be. And this boom plate is now at a weird angle. Looks like it's just jammed up against the ceiling. It's tight on one side, has a huge gap on the other, and that's just a visible defect, visible from everyone that walks into that room. This kind of illustrates how much operating room design really is a game of a fraction of an inch. There are so many specific conflicts that can come up in an operating room, whether it be where the lights are, how the lights are mounted in the ceiling, where the boom plates are mounted in the ceiling, how big they are. There's all sorts of details that you need to be familiar with regarding each individual vendor's specs and the model that they're using and the exact sizes of everything, because one small oversight can lead to some pretty obvious defects in the finished product. Another consequence of kind of rushing through a design or just getting a design on the paper is a design that could look like this, where somebody decided to just put diffusers all the way in a ring around the surgical or around where a table is going to be in the middle here. And the result of that is, one, it doesn't meet code, but two, it's not doing anything to protect that patient. So that 30% risk of infection from airborne transmission is not being mitigated at all with a design like this. And then finally, I think the most obvious consequence of any risk is change orders. And really the name of the game here is just doing everything you can to catch those conflicts ahead of time so that you don't give a contractor the opportunity to buy a boat that's literally named change order. So there's it's kind of a catch-22 in some scenarios. You can put a ton of time into developing a fully coordinated design and mitigate the risk as much as possible, but that leads to extended timelines, longer bid dates, because it just needs more time to put everything together. And it can give you personally as a designer the appearance of decreased productivity and inefficiency. And that's kind of the name of the game in the design world, is still you're trying to accomplish a good design in as little time as possible and be efficient for your partners, your clients that you're working for. But that comes with a level of risk associated with it, even if you put a huge amount of time into it. And this risk can come from things that are outside of your control. For example, there's always a little bit of risk in here that an ownership group might change the boom vendors they want, the imaging equipment vendors they want, the boom locations. You know, a surgeon could come in at the last minute and demand some last minute changes. And at that point, what do? You're supposed to reinvest all that amount of time back into it to get another good design at the end of it. On the other hand, if a design kind of gets rushed, there's a significant amount of risk that's associated with that, such as loss of reputation and trust, where if you have designs that have those conflicts that I showed you earlier, that's going to be a thorn in the ownership side for a long period of time, for basically the life of that room. Another thing that can happen is those initial savings that you made by cutting down on the time put into the design, or the initial cost of the whole system, can quickly evaporate by any conflicts that come up. Now you're talking those change orders and more design time that's really going to rack up the cost to probably be as much or more than what you were trying to avoid. That's illustrated here. Again, even more time committed to any fixes, frustrated ownership, and then again, unnecessary risk to any patient entering the OR if that design isn't accomplishing what laminar flow is there to do in the first place, which is keep patients safe. So our question is, how can you have your cake and eat it too? How can you mitigate the risk as much as possible while not pouring an inordinate amount of time into your design of your operating rooms? Well, our answer is by working with us, we can provide a fully coordinated package with exactly the same inputs that you'd be working with, except really you don't have to lift a finger. We would take all the inputs that you start with, such as, all right, how big is the room? How much air is going in there? Where's the general ductwork coming from? What are the filtration requirements of the ownership? Where are the structural beams and any connection points or any low beams that might be running through the space and getting in the way? All the way through to where are med gas conduits, electrical data lines, and temperature requirements. What are the heat loads of the room? We take all those requirements, pass it through our process, and provide a recommendation of the most appropriate system for any of your rooms. We're not going to try to jam one system down your throat to fit all the types of rooms you have. We're going to tailor each room and each project according to what the specified needs are. Do you want future flexibility? Do you want it to be as cost effective as possible? Do you want to integrate with structural equipment that's hanging from the ceiling? Do you want to manage the temperature of the space? Do you want ultimately 0 particles around that patient and complete patient protection? Whatever our recommendations come out to, we work back and forth with you to see what's going to fit your needs best and the ownership's needs best. And then we provide a fully coordinated system that fills that space and coordinates everything within that space. Booms, lights, med gas, everything included. Really what's going on here is after we work out these recommendations, Holden, who is gracious enough to host this, becomes our listening post. They keep us up to date on any changes that may be coming down the pipe, such as imaging equipment vendors changing, or boom vendors changing, or boom locations changing. They let us know. We can turn around a design in a matter of days and get you something that you put on the plans and is fully coordinated with everything else that's in that space. So you're not restarting your entire design process anytime a change, even a change that's out of your control, happens. What's going on behind the curtain there a little bit is we'll look at the room, look at where some boom locations might be, and provide a design that first and foremost is meant to protect the patient as much as possible. Now we'll check the box of complying with ASHRAE 170, and I'm going to look at what ASHRAE 170 specifically requires in a second here, but we'll check the box of ASHRAE 170. But what we found is that designing to the minimum of ASHRAE 170 really doesn't provide any patient protection at all. You know, if you design strictly to the minimum, you might as well not have laminar flow at all. So we'll check the box for you, but also make sure that we're providing as much actual patient protection as possible. We'll then coordinate that entire system with all the other equipment that's in the ceiling. We're not just looking in one lane. We're not just looking at, all right, how do we fit the air in here? We're looking at how the air best fits around all the other equipment in there and how our ceiling system in general can provide access to all those needed services in that space. So for example, if we're looking at a room here that has imaging equipment hanging from that ceiling, they have ceiling level unistrut running across that needs to support all this. We're coordinating where those rails are with the imaging equipment, not putting diffusers over those rails. And then we also actually are looking at other electrical components that are associated with this imaging equipment, such as where are conduit drops that need to go to that equipment, where are microphone drops, where are the booms, where are access panels for all these things, where are lights going to be housed. This system really touches everything. And so as a result, we need to coordinate everything together into one large system that satisfies all the requirements of everything in that ceiling. We'll provide drawings that again are not just looking at the air, but also where everything else lands within that. So we're documenting where boom locations are going to be relative to isocenter and where all of the other equipment is relative to everything else. We'll then provide drawings that show where all the structural is going to be, such as this ceiling level unistrut, where these plans are going to go, what the rough ceiling opening is, and then we provide a map of how that puzzle piece goes together with all the modular subsections that actually end up going into that ceiling. Along with this, there's a huge benefit that comes into us after bid day too. So not only are we providing a fully coordinated design up to bid day so that everybody's talking apples to apples and we want to know what we're talking about, but actually after that date, we provide several services where we will come on site, actually measure the locations of all the structural equipment and ceiling openings, anything that needs to be done before our system actually gets on site, and either redesign our system if need be, or provide the checklist of what needs to be adjusted in order for everything to go as seamless and smoothly as possible. So for example, we can take a room that may look like this, where everybody's just trying to get their stuff in wherever it can go. We'll actually coordinate directly with all the other players, such as the boom vendors, the structural engineer, general contractor, ceiling opening, everything there. We coordinate that entire space together and make it into one large integrated ceiling system. Some testimonials from other people that we've worked with across the country. And right here, there's no risk in buying from Precision Air. We mitigate that risk as much as possible while mitigating any design time required of you. All you need to do is send a couple emails, answer questions, and we get a fully coordinated design back to you. And other architects says we didn't have a single RFI during any of these projects. Nobody else is so proactive at catching conflicts between trades and guidelines, and the end result is so perfect that it's worth it every time. Now, that's our process, but what are the actual components that I'm talking about? When we're designing systems, we're going to provide recommendations as to what is going to be the most cost-effective and patient-effective system for this room. So the first and most fundamental system that we have is called Surgicare Flex. And what this is an integrated ceiling system that includes framing, diffusers, access panels for above ceiling access, boom penetration panels, and lights, all in one clean package. So that from the room, it all looks like it was meant to be there. Every boom location is coordinated to exactly where it's going to be to fit inside the system. And there's none of those unprofessional looking conflicts at the end. A quick illustration of how an integrated ceiling system goes in as opposed to just individual diffusers in a sheetrock opening. Here we're going to look at an operating room under construction. Here we have one large ceiling opening. Those puzzle pieces, the modular framing sections, are prefabricated, pre-coordinated with all the openings and where everything is going to be in each of those openings within it. It's gasketed, fastened together, lifted up into the ceiling, hung by typically just hanger wire or gripple. Those diffusers are mounted in locations predetermined and pre-coordinated. Duct connections are made. Now your accessories like your access panels and boom penetrations and lights are laid in. Those pre-coordinated, pre-dimensioned boom locations are cut. Room side replaceable HEPA filters are available. Those booms get mounted and you're done. A typical operating room with individual openings for everything might take a week to get installed. This system takes about a day with a crew of 2. Now, sometimes designers have been turned off by integrated ceiling systems, primarily because it looks like it is a higher initial cost. But the overall cost of the project is actually about 20% lower because it cuts down on labor so dramatically. If we're comparing 2 basically identical designs, but one of which has sheetrock crisscrossing through every component here, so you have individual openings cut for every single device and big gaps between everything. Doing that versus one large ceiling opening with the modular subsections and predetermined locations popped in there actually results in 20% lower cost. Now, this is the primary reason why most of the country, except for kind of the northern Florida, Georgia, Tennessee area, has adopted integrated ceiling systems because they are less costly. Even if you are in an area that has uniquely low labor rates, kind of the worst scenario is that it's going to come out to a wash, but you still get those added benefits of it being a flexible, fast turnaround design that didn't eat up a ton of design time and is at a much lower risk of having any conflicts throughout the entire installation process. Another variation of an integrated ceiling system is our plenum system, which instead of having individually ducted diffusers, all this is one large plenum that is mounted integral to our framing, integral to the diffuser bodies themselves, and allows you just to lift these subsections in place and not have to fish ductwork into this area at all. Allows you to provide connections just to the outside, and we handle that final air distribution to the entire space, basically keeping your HVAC concerns to zero inside this entire area. These systems come in, again, those modular subsections, very easy to lift into place. You know, heavy lift equipment required, no forklifts, genie lifts, anything like that. These can be lifted up. I've seen people install it with stilts. And so it can, depending on the space that you're talking about, it can be very useful. But like I said, during our design process, we're going to provide recommendations of what is really the most cost-effective and best way to go about things. A lot of engineers get excited about plenums really quickly because they see that initial benefit of not having to fish individual duct connections in. However, very often we might come back and say, hold on, you could do better, be more cost-effective, and actually avoid conflicts better with a system like this that has just side inlets or special customized sizes within this, because every room is different. Every room is customized and designed for that specific space. And so this could actually be much more cost effective than a plenum. So basically what we're doing is preventing designers from jumping to conclusions that might not actually be in their best interest at the end of the day. When it comes to rooms that have imaging equipment, which is a growing popular kind of setup, a hybrid OR is becoming more and more popular in hospitals across the country nowadays. How do we integrate with that ceiling level unistrut? How do we keep this all as one complete unit, but still have structural elements now mixed into it? How we do this is actually provide framing members that integrate directly to that ceiling level unistrut with prefabricated hanging tabs. Now, what's unique about this is that it allows you to hang that framing directly off that unistrut. It's at a predetermined height, so it can't be accidentally hung too low or too high and get in the way of the medical equipment, causing another conflict. It is easy to install in that it just snaps and sits on top. It can be scooted around and adjusted. And then you don't need to send fasteners into that unistrut and fasten it that way. One big problem that can come up is if people are just trying to put sheetrock or even diffuser frames right into this unistrut, is that most people will actually drill from this lower channel into the lower channel of that unistrut. Now what happens there is you have a bunch of screw heads that are poking through into that unistrut, and when the imaging equipment vendor comes to install their equipment, they can't fit their blocks into that unistrut. Their blocks need to slide freely, basically in this bottom channel, to allow them to mount their imaging equipment. If you have a bunch of screw tips poking into that, they might have to burn a whole day just chiseling off those tips in order to get their equipment in to begin with. If you ever have experienced a design delay that caused an imaging equipment vendor to have to reschedule, usually they're out a good another 3 months before they can get back out and finish the job. So avoiding that at all costs is a major benefit of this system. Again, these systems can be installed by a crew of 2 in about a day. In fact, we had one project where the contractor only had 1 person show up that day to install this system, and our factory services were down there to supervise the installation along with a rep, and actually they ended up doing most of the labor. The rep was able to install this system. That's how simple and easy it is. It's not a long learning curve at all, and it's actually probably easier than the individual framing openings for each diffuser mixed in with this unistrut. Now, a way to further incorporate even the structural and electrical conduit into this package is with a solution we call Monoflex. Now, those other systems I just talked about really are talking about everything at the ceiling level. So whether that be unistrut, framing, lights, air, everything is sitting at the ceiling level, but everything that's above the ceiling still has to be coordinated between structural engineers, electrical engineers, where their conduit is going to go, and the support of all those medical equipment hanging from the ceiling. An interesting solution to that is this Monoflex system. What this is a structural grid suspended about 11 inches above the ceiling that allows you to mount a boom literally anywhere within this entire array. Right above that is a electrical raceway that allows you to bring conduit and med gas just to the edge of that array, and this then handles the distribution to any of the devices requiring it within this. So what do you have? Equipment boom, anesthesia boom, just a light boom. All the power and gas and plumbing runs through this raceway, allowing you to avoid that coordination headache of fishing those lines through this entire system. It basically gives you the same benefit of a plenum, but with all the other services that go into that space. Above that, we can also include a HVAC trunk duct. Now, from the perspective of an engineer, this essentially works the same as a plenum. Now, all you have to worry about is bringing your air to the edge of this array, and we take it from there. We coordinate the individual connections down to all the diffusers so that you don't have to worry about any of that coordination within that space. The reason that we do this system with individually ducted diffusers and not a plenum is that a plenum inherently limits your flexibility, both during the construction process and well after the construction process. If you put a plenum in that space, you really are owning about 20 inches above the ceiling with just a big air box. That allows you, or doesn't allow you, to change any boom locations without having to go through really a redesign. With this system, you can rearrange these boom plates anywhere you want within this whole ceiling area, and then very easily and quickly rearrange any of these other ceiling level components, such as the diffusers and lights and so forth, on the fly, without having to remove an entire subsection or redesign an entire subsection of that grid. This system comes with boom mounting plates, a universal mounting structure that accepts any type of boom vendor, any type of boom model onto that plate, allowing you to change between a single boom and a tandem boom at any point during the construction process. And it also includes the connections all the way up to the deck. So it's the only true ceiling to deck solution. We're not just providing a structural grid that means that you have to have a structural engineer figure out how to suspend this now extra heavy structural system. This includes everything all the way up to the deck. A unique benefit of this is, say we're looking at a construction project where they just want a single, the owner just wants a single boom in the middle of the table. All right, we've designed the system, it's great, and we're getting ready to install, but then at the last minute, the ownership comes and says, hold on, we want 2 booms here. 1 boom isn't gonna cut it, we changed our requirements, we want 2 booms. Normally, you'd have to go back to the drawing board, refigure out all your structural supports, and reconfigure the entire ceiling array to match that change. With this system, it can accept that change on the fly. You can add another boom plate here without any disruption to the construction timeline. And this is because this grid allows you to mount a boom plate anywhere within that entire array. So even if this system can actually be installed essentially immediately after demolition and can accept any changes all the way to the completion of the project. Now let's take it a step further though and ask, all right, what if 2 or 3 years down the road, the ownership wants to make this operating room a full-blown operating room. It's going from a procedure room to a full-blown operating room. So, hey, we need to add 2 more booms. Normally, you're talking about another renovation project. However, with this system, all you have to do is put a couple more boom plates in there, mount it to the grid that's already existing, no cutting, no welding required, and then you just rearrange the ceiling system with those individual components instead of removing an entire subsection of a plenum. This can allow you to really not have to renovate an OR for decades after the project is completed. This allows you to do a renovation over a weekend, add new boom equipment, add new medical equipment. This also works with rooms that have that ceiling level imaging equipment, hybrid ORs. This allows you to do those remodels in a matter of days instead of having that OR be down for months. Some side-by-side comparisons here. Here's that traditional room of individual diffusers, individual booms, conduit, and HVAC fishing into every single one of those components versus this system where it's one complete package and all you got to do is bring your surfaces to the edge, and we take care of everything within here. This is what I mean by ceiling to deck solution. So this system includes all the ceiling level lights, diffusers, framing, that structural grid, all the way up to that deck. So anything within this space is really out of your hair for the life of the room, as opposed to some of the competitors, which may provide a structural plenum. But again, that structural plenum does not include the scope all the way up to the deck. This is still somebody's time, effort, and extra cost associated with suspending that system. Everything in red here on this project actually costs about an additional $25,000 to $30,000 per room just to support what was supposed to be a structural package. Another additional option that's available with us is visible light disinfection. So we partnered with a company called Vive, and what they can provide is a light that is in the ceiling of your operating room that is visible light that is killing bacteria 24/7. It's not UV, because if it was UV, nobody would be able to be in the room. This is visible light, a specific wavelength of visible light that is actively killing bacteria and viruses. And so people can work in it all day long, and it is continuously lowering the baseline level of contamination in that entire room. This is kind of the graph they show compared with daily cleaning. Normally with daily cleaning, the dirtiness comes back up to the same level it was every day, and then it gets dropped back down and the cycle just repeats. By putting this antimicrobial lighting in there, you're lowering that overall baseline contamination, lowering the risk to everyone in that room from both COVID and surgical site infection bacteria. One thing to note about this is it's not a active defense system in that it can't zap a bacteria that comes off of a nurse before it gets into that patient. It needs a longer exposure time to kill any of that bacteria. So you still do need that active air defense system, keeping that bacteria from landing in a wound, but this helps lower the risk of anything being kicked up and added to that level of contamination in the space. Now, here's where we're going to dive into kind of the surprising science of how air actually moves in an operating room. ASHRAE 170, as I mentioned, is the code that governs how airflow needs to be designed in an OR. What they do is they define a critical zone, or what we call a critical zone, which is the table footprint plus a 1 foot perimeter outside of that table. So you have a critical zone here, and your primary supply of Group E non-aspirating, aka laminar diffusers, need to be above that space. However, when ASHRAE was writing this code, they understood that everybody else also wants to be as close to that table as possible. Everybody wants a piece of action above that table. And so they said, all right, there's no way we can claim all of this space for ourselves. We need to give room for booms, lights, med gas, other people to get in there. And so they said, all right, of that critical array, 30% of it may be inactive. Doesn't have to have a diffuser there. It can be a boom, a light, or whatever else you want. So you could drop this diffuser out and be perfectly fine from an ASHRAE standpoint. Now, where did that 30% come from? How do you know that if you have 30% inactive, you're still safe? Honestly, your guess is as good as mine. I've never seen any backing of why 30% is acceptable, how that impacts patient safety or anything. It's kind of pulled out of a hat. That's kind of the first point here, indicting the ASHRAE 170 code for not necessarily being best practice. It is a design guide. It is not a performance-based standard. That gets more evident when you start looking at some of these other points here. The minimum design velocity of 25 to 35 CFM per square foot. A CFM per square foot is not exactly a unit of velocity. The math comes out to feet per minute, but it's written in the code as CFM per square foot because they wanted it to simply be a design guide where you could say, all right, I have X amount of CFM divided by Y amount of nominal square feet of diffuser. I fall within this range, therefore I'm good. This is not meant to be an actual metric that is to be measured. They didn't want somebody coming in with a device and actually measuring how fast the air was moving out of the diffusers or even around the patient. It's simply a design guide. And that gets more evident when you skip down to the bottom here. If you look at the filtration requirements, minimum filtration was MERV 14, which only stops 75 to 84% of particles from reaching that patient. So there's no way that you can actually predict how clean the air is going to be in that room by designing to ASHRAE 170, because the cleanliness of that air is totally dependent on how clean the air you're filtering is to begin with. You're not filtering it with HEPA filtration all the time, and so you could still be delivering contaminated air directly over that patient. Now, recently, in just the past few weeks, ASHRAE 170 actually updated their code for 2021 to say that the minimum filtration into an OR must be MERV 16, so 95% effective at the 0.3 micron size, which, all right, is a step in the right direction. Still not HEPA, still 100%, but in rooms that have orthopedic procedures, transplants, neurosurgery, they have a specific list of critical surgeries. Those rooms must have HEPA filters in the diffusers per the new updated code. So they're moving in the right direction. But now the question is, all right, even if you have HEPA filters in the ceiling, how much is a design like this doing to protect the patient? To test that, we actually created an operating room in our office and designed it looking like this, with a 8-foot wide by 12-foot long array of HEPA filtered diffusers packed as tightly together as possible, basically creating a perfect design. We surrounded that array with lights and put booms in the light ring on the outside here. So we have 1 boom, 2 boom, and all of these diffusers have a HEPA filter within them. So we know we're delivering clean air right out of the ceiling. We're operating at about 25 air changes, so exceeding the ASHRAE standard in that sense. We're at about 27 feet per minute, so we're exceeding the standard in that sense. And essentially, we would call this an ideal perfect design, 100% critical zone coverage. We're not even playing with that 30% free area that you can get. We have the most ideal design possible. To test how effective this was, we took particle counts on the perimeter of the room and then compared those with particle counts at the patient. Each one of those comparisons is a dot on this normal distribution curve. And what we found is that with this design, you're stopping about 60% of particles that are in the room from reaching that patient. If you get lucky, maybe you can stop 70, but on average, you're stopping about 60% of particles. Okay, so laminar flow is doing something. You're reducing the number of particles that reach that patient. Every one of those particles is a potential contaminant that could cause infection and contribute to that 20 to 30% infection that comes from the air. Now, what happens if we play with the design a little bit? If we move one of those booms in just 2 feet, still not encroaching on that critical zone defined by ASHRAE, we still have 100% critical zone coverage. But just by moving that boom in 2 feet and having this area be inactive, you've cut the performance in half. Now you're only stopping 30% of particles that are in the room from reaching that patient. You take it one step further and move both booms in to the same distance from the table, still not encroaching on that 100% critical zone coverage. You've effectively eliminated any protection that laminar flow is providing to the patient. 0% of particles in this space are getting stopped from reaching that patient, even though you're exceeding ASHRAE in every possible sense. This is what I mean by ASHRAE not being a performance-based standard or even best practice. You can do much better than ASHRAE very easily. And we're here to show you why, or here to show you how, and we want to be a part of your projects to show you how you can get this clinical benefit while still handling all those other construction risks. Now, the question here is, even with this perfect design, how am I getting particles at the patient? I have HEPA filtered air coming in through the ceiling. I know it's as clean as can be. If I put a particle counter up to that ceiling, I'd basically be reading zeros almost all day. However, by the time the air gets down to the patient, it's contaminated and dirty. If I have laminar flow, that laminar flow should be coming down in smooth streamlines all the way around that surgical area, not allowing any contaminants in. Unfortunately, our understanding of laminar flow is currently flawed. Because the laminar flow is just a passive device smoothing the air out as it passes through, it may be laminar for the first couple inches out of the ceiling, but it quickly takes a dramatic turn and an unexpected turn. What's happening here is that the air coming into the space is responsible for controlling the temperature of the space. There's a lot of heat, people, equipment generating heat in the space. So generally the air coming in needs to be about 10 to 12 degrees colder than the air already in the room. Because that air is so much colder, it's more dense than the warm air already in that room, and it gets acted upon by gravity and accelerates towards the ground. Because the air in the center can take a clean shot straight down and basically fall straight down, but the air on the edge of the array actually gets resistance from this rising warm air and gets pushed inward, following the rest of that cool air down. As that air moves inward and down, it is continuously accelerating because it's still dense and cold, and that actually creates an entrainment or an induction effect that pulls in this contaminated warm air and gives it a free ride into that patient. This is where all those contaminants are still coming from, even though you have a perfect design and HEPA filtered air coming in. The other side effect of this is the patient is now receiving the brunt of the cooling. On average, what we've seen is about a 6 or 7 degree temperature, 6 or 7 degree difference in temperature between the patient and the surgeon in terms of air temperature, because the patient is receiving the brunt of this cooling and it's actually moving very, very fast by the time it gets onto the table. It leaves the ceiling at about 25 feet per minute, and it's about 125 to 150 feet per minute by the time it gets down to the patient. Meanwhile, the surgeon isn't feeling any of that direct cooling effect because the air is just missing them. To solve this problem, we knew we needed to take a higher level of control of all the properties of the air. You can't just smooth it out. All of our standard systems, all of our competitors, anybody out there, all they're doing is smoothing the air out and not controlling all those other properties. In order to control those, we created what we call Surgic Air Zero. It's the world's first and only zero particle system that can create a zone of zero particle sterility around the patient and the surgical team. Now, to show how well this works, we actually installed 3 of these systems at a orthopedic facility here in Minneapolis called TRIA. And after a year of using the 3 rooms, they invited us in to take particle counts and actually monitor the particle counts right at the table during an entire knee replacement procedure, film the entire thing, and then interview the surgeon afterwards to see what they thought of it. This is the result of that video.
TRIA Orthopedics is a leading comprehensive center for orthopedic medicine in the Minneapolis-St. Paul metropolitan area. When TRIA was designing new operating rooms, they decided to construct a facility that matched their commitment to the highest possible level of patient care. To help eliminate the risk of surgical site infection, TRIA took their operating room design beyond what most healthcare organizations consider state-of-the-art and reached a level of patient protection that most considered impossible.
So my name is Gavin Pittman. I'm one of the orthopedic surgeons here who does predominantly total joint replacement. We'll take more or less any step we can to minimize the risk of having somebody develop an infection, especially from contamination in the operating room. We can clean the surfaces of the OR very easily. We can clean the floors and we can clean the lights and so forth, but keeping the air clean is something that frequently would be beyond your control. The less particles that are floating through the air near the operative field certainly is going to decrease the risk of contamination during the surgery.
To guarantee results, TRIA turned to the only company that could eliminate all particles from the air in the operative field.
I'm Ted Folstad with Precision Air Products. I am the Vice President of Engineering and R&D. I have been intimately involved in all aspects of the development of the Surgic Air Zero system. At Precision Air, we believe every OR in the U.S. should have zero particle air.
For over 45 years, Precision Air has been the leader in operating room airflow control. Extensive testing in Precision Air's in-house research lab identified inherent flaws in current OR airflow techniques that actually contribute to surgical site infection, a finding that current literature confirms more each day. In all current ORs, laminar flow actually draws particle-laden air from the perimeter of the room and delivers it directly over the patient. Even with the best filtration available, the operative field is continuously flooded with contaminants. To solve this problem, Precision Air created Surgic Air Zero, the first and only system to achieve and maintain zero particles in the operative field. Surgic Air Zero is a comprehensive air control system that can protect the patient from both activity in the perimeter and contaminants generated by staff near the table, as demonstrated by this real-time particle count during surgery. While particles and bacteria are continuously shed by everyone in the room, none of them reach the patient. There are no air cleanliness regulations for operating rooms and no prescribed number of particles that are allowed to reach the patient. Precision Air, like TRIA, decided that the only acceptable number of particles is 0.
When that particle counter drops to the true zeros, straight zeros, everyone that sees that is absolutely astounded. And it is a remarkable level of performance.
The main benefit long-term is to minimize infection risk, and we're a year into doing outpatient hip and knee replacements in this facility, and we have not had any infections. So I think we can use that as a barometer that this system seems to be working well.
Most engineers, administrators, and physicians would agree that even if one surgical site infection is prevented, the investment in Surgic Air Zero will have been worth it. Surgic Air Zero is a revolutionary achievement in patient protection and the only measurable performance improvement in OR airflow in over 30 years.
There is no doubt in my mind that ultimately this will become the industry standard for any facility that strives to be a center of excellence.
See for yourself how Surgic Air Zero can reduce infection rates by eliminating surgical site airborne contaminants at precisionairproducts.com. Why settle for less when you can have zero?
Now, the difference between Surgic Air Zero and any other typical laminar flow system is that it's a comprehensive control system. It's no longer just diffusers in the ceiling of the array, but it actually includes fans, coils, and a control package with sensors sprinkled throughout the entire system, with a control panel actually at the fingertips of the staff in the room, allowing them to manage and finally take control over their operative environment. What we're doing here is actually tripling the amount of air that's going into the room, tripling or 4 times the amount of air that's going into the room. So we're delivering air through a HEPA filtered array, and instead of sending all that air back to the hospital or to the air handler, we're actually taking most of it, bringing it through a pre-filter, and bringing it back to what we call a mixing plenum here. We're mixing this with the required air changes from outside per ASHRAE, reconditioning it, pressurizing it with the fans, and redelivering it back in through those HEPA filters into that room. This is how, when I said that you can feed us temperature or heat load information about the room, and we can take care of it from there, this is how we can do that. You no longer need to worry about the heat loads and temperature issues in the room, because we're handling that locally to the room with our system. Because we're recycling the air locally from that room, we actually don't even need the required 20 air changes from ASHRAE anymore from the house. We actually could get away with 10 or 12, or theoretically, if you have a DOAS unit or a high efficiency dehumidification system, you could get away with giving us the 4 air changes from outside. And we've had some studies that show that this actually can lower the energy requirements for a surgical suite by up to 30%, simply by putting the system in there, and you get that added benefit of 0 particles. This is what the airflow looks like with the Surgic Air Zero system. Now, all the contaminants that are in the space can't get into that room, because since we're tripling the airflow into the space, we're reducing that delta T, or the temperature difference between the supply air and the room air. Now, instead of delivering air at 10 or 12 degrees colder, we're only delivering it at 2 or 3 degrees colder, eliminating that effect of gravity and the entrainment problem, and maintaining this wide zone of clean air throughout the entire surgical area. The added benefit here is, since this air is warmer, it's actually warmer air hitting the patient, reducing the risk of hypothermia for them, and it's actually cooler air actively hitting the surgical team, meaning they're more comfortable and the patient is safer. Other added benefit here is since we're delivering so much more air into the space, the entire room becomes cleaner much faster than a typical operating room. We're dropping or diluting the air in there so much that all the smoke and everything actually reduces the exposure of smoke to the staff by 75%. Some further evidence of this is we have a lab, or operating room lab in Minneapolis here. Anyone is welcome to visit it and actually see this for themselves. Right here, we had 25 guests in the room. None of them are scrubbed, gowned, anything. We have a door open to the dirty office outside, and still that particle counter at the patient is reading zeros. The overall effect of this is the only study I've ever found that actually differentiated between laminar flow systems was this one that came out in 2020. They looked at 50,000 total knee replacement procedures over a 10-year period and compared conventional ventilation, as in turbulent ventilation, with the low volume laminar flow, which is basically what ASHRAE standards are, low volume flow. And they compared that with high volume, which is what Surgicare Zero is working under. With the high volume systems, they found there's a 20% lower risk of revision in any rooms that had those systems. Statistically significant, huge sample population, and they were able to statistically find that there's a lower risk of infection, which conveniently matches the risk of infection from airborne contaminants that we saw earlier, the 20 to 30%. I'm short on time, so just quick show you, this system also gives you the ability to rapidly control the temperature of the space. You can heat 10 degrees in 5 minutes, cool 10 degrees in 10 minutes, and that's because we're doing all of this local to the room. We're not relying on the system far away to serve this space. And here's what I was talking about with that dilution of the air, where a traditional contamination event with traditional laminar flow has a huge peak in contamination in the space, takes a full 20 minutes for it to go back down to normal, versus with Surgicare Zero, cuts it down by 75%. So that's the surprising truth about how air actually behaves in an operating room and what you can do about it, and also a better way to minimize risk and minimize time investment in the design process of really any room, whether it's zero particles or not. So Tracy, I'll